equations for Physics 2211. For this lab, I first uploaded a spring and mass oscillating and tracked its movement as the mass oscillated in the x and y direction on tractor. After obtaining this experimental data, I constructed a code on GlowScript to predict the motion of the same spring using Newton's second law and the energy principle. For this lab, some relevant equations and laws that I utilized for coding included the magnitude of spring force, the magnitude of the gravitational force, the position update formula, and the velocity update formula, both derived from the momentum principle. I also used relevant equations derived from the energy principle, including change in total energy, change in kinetic energy, and the change in potential energies. The equation for kinetic energy, the equation for potential energy on Earth's surface, and the equation for spring potential energy all derived from the energy principle. Here is the video of motion I observed on tracker. You can see tracker generate the graph for x position versus time. The zigzags of the graph accurately portray the oscillations of the spring as the video progresses. Before coding our observations into the predictive model, we have to consider the assumptions and observed values obtained through tracker. We first assume that the system includes Earth, the spring, and the mass, and that this system is closed. This allows us to set delta E equal to 0. The mass of the object is known as 0.402 kilograms. The object starts from rest, so its initial velocity is 0 meters per second, and L hat is equal to 0.7 meters. And from tracker, averaging each period of oscillation, we get an average period equal to 1.6 seconds. By plugging the values for mass and average oscillation period into the equation for spring constant, I obtained a K value of 5.9 Newton meters. Using the known value of L hat, we can solve for the relaxed length of the spring, or L naught, using the magnitude of gravitational force and the magnitude of the spring force. Since the spring is relaxed, we can assume the forces are at equilibrium and net force equals 0. This allows us to set gravitational and spring force equal to each other, isolate L naught, and plug in the known values of L hat, mass, the gravitational constant, and the spring constant to get a relaxed length of 0.0377 meters. First, to code, I updated the initial conditions of the ball's mass and position synonymous to the ones in tracker. After, I then coded each potential and kinetic equation used for the system's energy change. I then coded the motion of the ball for each calculation loop by coding motion using the position and velocity update formulas. Here are the energy principle equations applied once more. After running the code along with my observed data from tracker, GlowScript created 3 comparison graphs for the predicted motion of the spring and the observed motion, as you can see here. On the change in energy versus time graph, we can see an oscillating delta K, delta UG, and delta U spring. Through all of these energies are oscillating throughout the spring's motion, we observe a constant delta E equal to 0. This portrays that our assumption of a closed system of Earth, the spring, and mass is true. In other words, no energy is gained or lost throughout the spring's oscillation. Therefore, a successful change in energy versus time graph is generated. As we can see in our model and experimental x position versus time graph, the experimental data seems to lose its accuracy as the model graphs for longer time. This could be accounted for by a number of things, human error and the use of an average oscillating period being 2 of those possible reasons. Similarly, but a little more extreme in the case of y position versus time, our model experiment and experimental data seem to lose more and more similarity as the time on the graph is plotted. This could be due to, again, an estimated time for oscillation periods, but also could fail to plot correctly the actual spring constant throughout the observation, causing the variance in the graph. To reiterate, our change in energy versus time graph satisfies the energy principle in this lab. Since we assume that delta E equals 0 due to the closed system, our graph shows that no energy was gained or lost in the system. This is synonymous with the energy principle. In other words, the graph satisfied that delta K plus delta UG plus delta US equals delta E, which is also equal to 0. Using tracker, I calculated the average oscillation period for the spring and the mass in both the x direction and y direction. As you can see, the period of average in the x direction is larger by 1/10 of a second than in the y direction. The reason for this could be the lack of gravity acting on the mass horizontally as opposed to it is vertically. The gravitational force on the mass in the y direction could cause the oscillation period to decrease as the spring spends less and less time moving vertically as it does moving horizontally.